So we're going to do some more chain rule problems here. We have an outside function here, and then we have the inside function here. So I should automatically be thinking chain rule whenever I see that situation going on. So when I take the derivative, first thing I do is I take the derivative of the outside function. So the derivative of 3 times something, I'm going to pull that 3 out front. And so I have something raised to the x power. How do I take the derivative of something raised to the x power? Well, the 5 comes out front, and then I subtract the 4 from the next one. But then not only do I do that, once I pull back this layer here, I need to take the derivative of what's left, and what's left is that inside layer there. That's my squiggle. So I'm going to take the derivative of that squiggle inside there. Okay? So what is this equal to? This is 5 comes out front, taking the derivative here. So that's going to be 5 times, and then raise that to the minus 1. So that's negative 4 there. And so I've got this inside staying consistent here. Now the second part is the derivative of that inside. And so the derivative of the inside is negative 2x. Okay. Now simplifying here, negative 2x times 3 times 5 gets me negative 30. Ooh, that should have an x with it. So sorry about that, but there should be an x there. All right, so there's an x here and an x there. So that's a mistake. I need to make sure I get that in there. Okay. And then next problem, I have taken the square root of 5 minus 3x. Now, the outside function, it might be a little bit hard to see at first, but it's the square root. Because remember, I have the rider and the horsey. So how many x minus 3's do I have? I've got one of them inside. It's implicitly understood that this is a index of 2 for square root. And so I can rewrite this as 5 minus 3x raised to the 1/2. Okay? And so whenever I do this, now I'm going to try to take the derivative of this. And so this is my inside function. And then something raised to the 1/2 is the outside function. So I'm going to take the derivative of the something first. So something to the 1/2 times the derivative of the inside function. The derivative inside function, that blop, is 5 minus 3x. So what does this equal? Well, I take the 1/2 and I bring it out front. And then I subtract 1 from the 1/2. So 1/2 minus 1 is negative 1/2. And then I multiply by the derivative of 5 minus 3x, which gets me negative 3. Okay? So simplifying here, I'm going to have negative 3 in the numerator, 1/2 or 2 in the denominator here. And if I have a negative exponent, what does that mean? That means I do 1 over to get the positive exponent. But raising something to the 1/2 is like doing the square root. So I'm going to put the square root in the denominator there. And that's my answer. Okay? So you need a chain rule whenever you're doing square roots like this. Okay? Now, one thing that I might note, really technically you're always using a chain rule. So if I had f of x equals x squared, I know that the derivative f prime of x equals 2x, but I'm technically using a chain rule. The outside function is something squared, and then I take the derivative of the something. The something here just happens to be, okay? The something here just happens to be the x, okay? So how do I take the derivative? How do I take the derivative of something squared? the derivative of that is equal to what? Well, the derivative of something squared is equal to 2 times something. The derivative of the something, well, what is my something here? My something is just x, right? What's the derivative of x with respect to x? That's just 1, right? So the answer is still 2x, okay? So chain rule works. It's implicitly understood. Even so, when my differential, the dx matches the variable I'm taking the derivative with respect to there. All is good. Okay. All right, it takes a little bit to get that erased, but we got it. Okay, so I want to take the derivative of sine of some stuff. Right, that stuff is x squared plus x. How do I take the derivative of that? Well, I have to first identify the outside function. The outside function is sine of something. So I'm going to take the derivative of sine of something, right? That something is x squared plus x. And then once I take the derivative of the outside, then it strips away the outside and I take the derivative of the inside. So I take the derivative of the something. So what is the derivative of sine of stuff? That's cosine of stuff. But what is the stuff equal to? It's equal to x squared plus x. And then the derivative of the stuff, what's the derivative of the stuff? Well, the derivative of x squared is 2x, derivative of x is 1. So this is 2x plus 1. So if I simplify this, I like to write this part first and then my cosine at the end. So I just swap those around. Okay, a times b is b times a. So that's all okay. Now let's take the derivative of e to something. E to the negative x cubed, okay? So I take the derivative of e to the stuff, that's the stuff, multiplied by the derivative of the stuff. Okay, the derivative of the stuff. What's the derivative of e to something? Well, it's just equal to e to that something, right? Okay, what's the derivative of the something? Well, the derivative of negative x cubed, that's negative 3x squared. Okay, and so I just write this first because I like to write that piece first. Same thing here. I like to have these polynomial looking things first, and then my transcendental functions I like to write after the polynomial stuff. Okay. What about this one? This one's a little bit different. Okay, instead of e, it's ln. So natural log, we need to remember what the natural log derivative. Natural log of x, when I take the derivative of this, I get 1 over x. Okay, so the natural log of x is 1 over that x. Now, this is not the natural log of x, it's the natural log of cosine. So it's the natural log of some stuff. So it's derivative of natural log of the stuff multiplied by the derivative of whatever that stuff is, okay? So you know that the derivative of natural log of stuff is 1 over the stuff, okay, just from the definition. And then the derivative of cosine, that stuff there, is equal to negative sine. So 1 over the stuff, what is the stuff? The stuff is cosine. And then the derivative of cosine is negative sine. So what is this equal to? This is equal to negative sine over cosine, okay, which is equal to negative tangent, okay? Very interesting there, all right? So if I put a negative on this, then that derivative would become positive, right? So very interesting there, and that will connect later in the class. Okay. In general, though, to help you out with these natural logs, anytime I take the derivative of natural log of something, I don't care what it is. It could be cosine, could be x squared plus 2x plus 17 million. Who cares, right? ln of something. is 1 over the something times the derivative of that something. Okay? So I don't know what the something is, but that's in general how that works out. All right? Let's do one more or two more, I guess, and then we'll finish up with this. So tangent cubed. Now, I need to figure out what is the inside, what is the outside here. So the inside is tangent, and the outside is cubing it 3 times. So the derivative of something cubed is equal to, well, it's bring the 3 out front, power rule, right? If I'm taking the derivative of something cubed, I bring the 3 out front, and then I subtract 1 from the exponent. Okay, and then I take the derivative of the something, so the inside function here. What's the derivative of tangent? So this becomes 3 tangent squared, and then the derivative of tangent is secant squared. Okay, just like that. All right, last one right here. So the derivative of natural log of 10x to the 4th plus secant x plus e to the x. Now, how do we do this in general? We do 1 over the something, right, times the derivative of the something. So I'm going to do that right here. So I do 1 over this. So it's 1 over the something times the derivative of the something. So what's the derivative here? So the derivative of 10x to the 4th is 40x cubed. And then the derivative of secant is secant tangent, and the derivative of e to the x is so easy, it's e to the x. Okay? So that's the numerator. And then this is the denominator. All right, guys, hopefully this helps you a little bit more in identifying what is the inside, what is the outside. And remember, the chain rule is an onion, okay? It's an onion. So we're literally trying to pull off layers. So what is the outside layer here? Maybe it's the cube. A layer inside here is the square, and a layer inside of that is the squiggle. Okay, so we work from the outside inward. We're working our way in until we get down to nothing left. All right, guys, good luck.